Hello, welcome to this video. This is 1-4 for AP Calculus, and we are going to talk discontinuities today. We've kind of already loosely talked about this idea of functions being continuous, right? If I can draw the function without lifting my pencil, it's continuous. But I specifically want to call out discontinuities in graphs. All right, discontinuities. They fall into two categories. The first category is non-removable. And category two is removable. Now, I'll go ahead and specifically call out the three types of discontinuities. They're right behind me on the whiteboard, so that way you see them this entire video. But I'm going to go ahead and first classify them in the category. So we have non-removable. And the two types of non-removable, the first discontinuity is jumps. Now, jumps disrupt limits, right? The limit from the left cannot equal the limit from the right. Now, a possible equation of this would be if I had something like f of x is equal to, let's do negative x squared for all x values less than 0. And let's do x minus 1 for all x values greater than or equal to 0. I'm just making up two functions split at 0, and I'm going to do a rough sketch of what this looks like. So for all the x values less than 0, we have a downward facing parabola, right? Cut off at 0. And then I have a linear function, x minus 1. Okay, that's shifted down 1. And then I have a linear function this direction. There's a discontinuity at 0. I have to jump, or this time not jump, I just drop down to the other piece of the function. Jump discontinuities are indicative of piecewise functions. Whenever you're given a piecewise function, be highly suspicious of jumps. Now, the other type of discontinuity that you are familiar with, especially in rational functions, are asymptotes. And I'll go ahead and give a rational function here, 1 over x plus 2. 1 over x plus 2. So we have a discontinuity at -2. The denominator cannot be 0. Now what happens is we get an asymptote, and I guess I'll extend it this way a little bit more. Here, let's say this is -2. I have an asymptote at -2. My denominator cannot be -2. Well, my x value, sorry, can't be -2. Otherwise, that makes the denominator 0. Okay, and so this function would look something like this. And we studied these extensively last year. We'll get you very familiar with those again. That's an asymptote. Okay, now alone in its own class, removable. This is the only removable discontinuity. I don't know why they just named the whole category after it, but that is a hole. A hole, wow, what a hole. This is when we have a factor top and bottom. That's exactly the same. So if I have a function x times x plus 3 and divided by x plus 3. I have a factor top and bottom that what we'll do when we reduce this, right, is those factors cancel. So here we have a hole at -3, right? If I set that equal to 0 and solve, we get x equals -3. So, okay, the reduced function is just f of x equals x. It's a linear function, looks like this. Except I have a hole at 3. I'll say here's -3. There's -3. And I have a hole. These are our three types of discontinuities. Jump, asymptotes, hole. Jumps, asymptotes, hole. Okay, that's the question. The key takeaway. What are the three types of discontinuities that we have? Jump, asymptotes, hole. Now we do classify them, and the AP exam and College Board will use these terminologies interchangeably, right? So they'll say identify the removable discontinuities or identify non-removable discontinuities. So you have to know which goes in which category. Now a hole, it is removable because I just kind of removed 1 point. Wouldn't you agree that I just removed that 1 point? That's the only discontinuity. So that's why it's called a removable discontinuity. We removed 1 point. Okay? All right. Example number 1. The graph above is f of x. Determine all x values where f of x is not continuous and classify each as removable or non-removable. So for these problems, what I love to go ahead and do is I go ahead and write, okay, removable. Boop, boop. And non-removable. Okay. Now I'm going to go ahead and I'm just going to look at my graph and I'm going to see, okay, where do I have a discontinuity? So I'll just go ahead. I'll start here. And I'll highlight. Do I have to pick up my pen to move? Nope. I had to pick it up. Okay, so right there at -1. Now what type of discontinuity is that? That's a jump. Very good. So that is a non-removable. So at x equals -1, that's non-removable, and that was a jump. Okay, let's go ahead and pick back up the highlighter, and let's go ahead and keep drawing here. Whoa, I'm going way up here. Oh, I have to pick up my pen. Okay, so that is a discontinuity. What type of discontinuity is that? Yes, that's an asymptote. I'm doing my best like Sesame Street. Okay, so that would be an asymptote, which is non-removable, okay, and that is at x is equal to +1, and that's an asymptote. Asymptote. All right, got it? Okay, let's go back to my highlighter. Okay, I'm going ahead and drawing. Oh no, there's a hole. Whoop. Okay, I don't care that there's a point below it. There's a hole there. I had to go over it. Okay, that's a hole. So that's a removable discontinuity at 3, right? Hole. And let's keep going ahead and drawing. Whoop. Oh, there's another hole right there at 5. Notice at 5, the function value is not defined. Not defined at 5. Not that that plays any part in what we're doing, but just wanted to point that out. Okay, so those are discontinuities. We have a jump, we have an asymptote, and then we had 2 holes in this example. The holes are removable. Jump and asymptotes, non-removable. Example number 2. G of x is equal to x squared plus 3x minus 40 over x squared minus 3x minus 10. List and classify the x values where g of x is not continuous. We have here, this is a rational function. A function that is pretty much a fraction. Fractional, rational, rational, fractional. The key thing that you're going to want to go ahead and do here is factor. I want to break down g of x. So I'm going to say, okay, g of x, in the numerator we have x, it looks like -40, that's 8 and 5. Difference of 3 will make the 8 positive and the 5 negative. Okay, so x plus 8, x minus 5. Then I'll go ahead and I'll factor the denominator -10. Well, I definitely want an x minus 5. I'm just knowing these problems, right? One of these factors is going to match. And then not always, always, you know, make sure you factored correctly. Okay, which I did here. So I have x minus 5 that cancels. Oh, what's that? Yes, that's a hole. Good job. So I have x plus 8 over x plus 2. That's my reduced function, x plus 8, x minus 8, or over x plus 2. Okay, so what happened? Well, we have a hole at x minus 5. So if I set this equal to 0 and solve, we have a hole at x equals 5. There's a discontinuity. I have a discontinuity there, okay? And then the denominator. I still have to worry about that denominator. It cannot be 0. So what value would make that 0? So x plus 2. I set that equal to 0 and I solve x is equal to -2. So you cannot have these values in your domain, 5 and -2. -2, this is an asymptote. So you should remember doing that in your studies of rational functions. We've identified two types of discontinuities. Now, a quick way to go ahead and do this, I guess if you're just asking about all discontinuities, is you could just take the denominator and set it equal to 0, and then you would be able to see all discontinuities. You don't want your denominator to be equal to 0, right? And that's what I did. I pretty much restricted here x minus 5 and x plus 2. Cannot be 0. Okay, I went a little bit extra there, but I feel like the context there and tying it into your previous learning is important. So what I'm going to go ahead and do now is I'm going to classify them. Okay, so I had a removable discontinuity at x is equal to 5, right? And this is a whole. And then we had a non-removable at x is equal to -2. And this was an asymptote. Not too bad. Okay. Example number 3. Whew. Consider the piecewise function defined below for h of x. Man, determine all the x values where h of x is discontinuous and classify each discontinuity. So, okay, I want to go ahead and figure out, I have a piecewise function. What did I tell you is indicative of piecewise functions? Jump discontinuities. So what I'm doing here, and I'm laying the groundwork. We're going to be doing this more formal in the next lesson. I have to be careful here at the cut point. Look, at -2, I want to make sure I don't have a jump, right? So what I'm going to do is I'm going to say, okay, what is the limit of h of x as x approaches -2? And let's do the left side. That first piece. So that's 2x minus 1. So all I'm going to do is I'm just going to plug this in. I know 2x minus 1 is continuous. Add this little note. Polynomials are continuous everywhere. Okay, so 2x minus 1, that's polynomial continuous everywhere. So I can go ahead, I can plug in -2 minus 1, and we get -5. Okay, so the limit from the left, that the function's approaching -5. All right, now how about the limit of h of x as x approaches -2 from the right? I'm going to use that right piece, x squared minus 9. Well, okay, I can plug in -2 here, squared minus 9. That's 4, take away 9, that's -5. Hey, they touch. Okay, so I know I don't have a jump discontinuity. They touch. All right, but we still have to watch out for holes, don't we? I could have a hole, right? So what's the function value at -2? Sorry, not f, h. What's h of -2? Well, I mean, didn't we just find that? Because it's equal to -2 here. Okay, so if I plugged in -2, which I already did, that's -5. Okay, so this is continuous. And I'm just going to add this note here. So continuous at x equals -2. They didn't ask us that, but your brain should register this. Okay, now we're going to go ahead and we're going to play the same game. At this cut point, at 1. I have to worry, oh, do I have a jump here at 1? Let me go ahead and investigate. So I'll change my my colors here. We're going to be writing a lot. Sorry, I don't know. Hopefully you didn't write in the middle. If not, get another piece of paper now. So as x approaches 1 from the left, what's happening from the left? So I have 1 squared minus 9. That gives me -8. Okay, and then I'm going to go ahead and say, okay, what's the limit of h of x as x approaches 1 from the right? 1 from the right. 1 plus. Now that's 3x plus 2. So 3 times 1 plus 2. That's 5. Hey, are those equal? No, they're not. They're not. So our function is not continuous. Not continuous. at that value. So what do they say? They say determine all the x values where it's discontinuous and classify. So we can say, and when this is a jump, right? So non-removable discontinuity at x equals 1. At x equals 1. That's like my summary. Okay? This is a jump. If you wanted to add in here jump, you could go ahead and do that. Okay. We looked at 1. We still have one more to go, and that is at 3. At 3. So I got to check this piece. Okay, is the limit from the left the limit of h of x as x approaches 3? Let's look from the left. So all I'm going to do, okay, and again, all of these are polynomials, right? This is a polynomial, continuous everywhere. This is a polynomial. All I want to do is just make sure, do they connect? Do they connect? So 3x plus 2. So 3 times 3 plus 2, that's 11. Okay, how about from the right? The limit as x approaches 3 from the right of h of x. That's just 4x minus 1. So 4 times 3, that's 12. Take away 1. Hey, it's 11. They connect. Okay. Oh, but now I got to watch out for removable discontinuities. Do I have any holes that are messing me up? And so what is h of 3? What is h of 3? Well, if I go ahead and I plug in 3, is my function ever equal to 3? No. H of 3 is undefined. What does that mean? Means there's a hole there. We have a hole. So we have a removable, that says removable, discontinuity, and I don't know why I capitalized that D. English people, don't crucify me. Removable discontinuity at x equals 3, and that's a hole. Okay, so, ooh, there we go. There's your summary. Okay, we'll formalize that manana. Okay, here is example number 4. This should definitely be a practice problem. Go ahead, pause the video, try this one. Is f of x continuous at x equals 2? Justify your answer. Is it? Pause the video. We'll go ahead and check it in a second. All right, welcome back. So for this one, again, is it continuous at 2? Well, again, I need to analyze what's the, okay, at my cut point, right, which is 2. So I need to say, okay, what's the limit as x is approaching 2 from the left of f of x? And all I'm going to do is I'm just going to plug in 2. We have 2 squared plus 2 minus 3. So that's 4 plus 2, 6. Take away 3 is 3. All right, now I'm going to go ahead and I'm going to say, okay, what's the limit as x approaches 2 from the right of f of x? Well, 5 times 2, take away 7. That gives us 10, take away 7, that's 3. Okay, the limit from the left is equal to the limit from the right. So we know we don't have any jumps, okay? Now, what is f of 2? I want to make sure I don't have any holes right there where they touch. Make sure that value is there. So when I plug in that value, notice we already plugged in 2, isn't it, this piece, because it's equal to here? So here the actual function value is going to be attached to my right piece. So that gives us 3. Hey, it's there. Now maybe you're saying, okay, sure, you talked about jumps, you talked about holes. What about asymptotes? Asymptotes really only come into play with rational functions. Like when I have a denominator that's a variable, right? I have to protect this, I have to protect it. Cannot be 0. Any zeros try to come, cannot be 0. Right? So here, x cannot be 0. Zero's coming your way, punch it. Okay? How about this one? Sorry if this is too violent for you. This video is rated PG. We just added a little bit form of violence. Okay, x minus 2. What value can't come in? 2. Okay, sorry. Can't come in. All right? Anyway, hopefully you get the idea. So I don't have to worry about asymptotes with these. So, okay, we say yes. Got to answer the question. Yes. f of x is continuous at x equals 2 because, now I didn't formally introduce this, but this is actually the justification. We would say the limit as x approaches 2 from the left of f of x is equal to the limit as x approaches 2 from the right of f of x, which is actually equal to the function value, f of 2. And it doesn't hurt if you want to throw in the value. You could say, hey, they're all 3. There's your justification. That's the definition of continuity, which we will formalize tomorrow. I know the limits. I know I don't have a jump, is what you're saying. Hey, reader, I know I don't have a jump. And then you say, which is equal to f of 2, the actual function value. Hey, reader, I know I don't have a hole. And it's all 3. That's the definition of continuity. All right, example number 5. Find the value for c that makes the piecewise function q of x continuous at x is equal to 1. All right, so I want to go ahead and make sure that it is continuous at 1. So the first thing that I'm going to go ahead and do is I'm going to say, okay, if it's continuous, then q of 1, that has to be defined, And I want my limits to also equal that value, right? Didn't we say that here? So I'm going to start with this as the easiest because q of 1 should be pretty easy, which is equal, if I plug in 1 minus 3, negative 2. I want my limit, and I want my, my function value to be equal to negative 2. Okay, so I already did the left piece, right? I mean, that's, as we're approaching 1 from the left, that's what the limit from the left is going to be. Okay, and then q of 1 is negative 2. So I want this. I want q of 1, which is negative 2, to be equal to the limit as x approaches 1 from the right. Well, that's just this value. That's the x squared plus cx minus 5. Okay, well, again, I have two variables. And I already know what x is. Isn't it 1? Okay, so negative 2. If I plug in, not negative 1, it's positive 1. Plug in 1, we get 1 plus c minus 5, which gives us negative 4 plus c. C is equal to positive 2. You could have went ahead to, and we've talked about this type of problem in the limit analytically and in the piecewise lesson. You could take the left and set it equal to the right and plug in 1. The limit from the left is equal to the limit from the right. But you also, too, you want to check and make sure that your function value exists at 1, which it does. It's attached to my left piece. Okay? All right. In this lesson, we went ahead and we talked about discontinuities. That should be the main takeaway from this lesson. What are the 3 types of discontinuities, and how do you classify them? Okay, hopefully you can read what's on the screen in front of you. And you know that jumps and asymptotes are non-removable. Holes are removable. That's going to do it for this lesson. Catch you in the next video. Give me a thumbs up, like my stuff, subscribe so you can get some more awesome math content. Catch you next time.